Hi everyone, my name is Alexey and I am glad to present our work DeepMark++, CenterNet-based clothing detection from Nizhny Novgorod Huawei Research Center, Russia. This paper focuses on clothing landmark prediction and clothing detection tasks using the DeepFashion2 dataset. The dataset contains 13 classes and the total number of unique key points is 294. The number of key points for every category varies from 8 for a skirt to 39 for a long sleeve outerwear. Our approach is based on recent CenterNet architecture. It solves two tasks simultaneously: object detection and key point location estimation. Let's have a look at the architecture. There is a backbone that downsamples input image 4 times to get a feature map. Then we further process this feature map to get object detections and corresponding key points. 13 channels in the center heatmap are used to predict the probabilities for each pixel being the object center for each of 13 classes. An object center is defined as the center of a bounding box. Ground truth heatmap for this contains Gaussian function generated in the object centers. Two additional channels in the output feature map, delta x and delta y, are used to refine the center coordinates. Both width and height are predicted directly as well. Another branch handles the fashion landmark estimation task. This task involves estimating 2D key point location for each item of clothing. Let's take a closer look at how it works. Just like in the original CenterNet, the coarse locations of the key points are regressed as relative displacements from the box center. So, if a certain pixel is classified as an object center early, we can take values in the same spatial location from this heatmap and interpret them as vectors to key points. To refine a key point location, a heatmap with probabilities is also predicted for each key point type. The local maximum with high confidence in the heatmap is used as a refined key point position. Similar to the detection case, two additional channels, delta x and delta y, are used to obtain more precise landmark coordinates. During model inference, each coarse key point location is replaced with the closest refined key point position. That way we can group key points belonging to the same object. One of the first steps involved in the solving key point detection tasks is defining the model output. The simple approach is to concatenate key points from every category and deal with each key point separately. Direct prediction of 294 key points leads to a huge number of output channels, 901. It's obvious, though, that certain clothing landmarks can be represented as a subset of others. For example, shorts do not require unique key points because they can be represented by a subset of trousers key points. The semantic grouping rule is defined as follows: key points with identical semantic meaning but from different categories can be merged into one group. This approach enables the formation of 62 groups and reduces the number of output channels from 901 to 205. The semantic grouping approach reduces training and memory consumption times by up to 26% and 28% respectively without accuracy drops. This reduction enables the use of larger batches during model training. We have also developed 4 post-processing techniques that increase the model's accuracy without compromising performance. It's clear enough that key point scores for the wrong category may have low confidence. We use this insight to recalculate detection confidence score using key point scores from the key point heatmap. The final detection confidence scores are calculated as a linear combination of bounding box score and average key point score. Note that certain techniques can increase mean average precision for key point location estimation and reduce mean average precision for close detection simultaneously. Bounding box detection and key point estimation results for the same object may have different I/O and OKS with the ground truth. For example, when bounding box was detected correctly, but key points were not. In this case, proposed technique involves lowering a score for false positive key points, which is advisable. The corresponding true positive bounding box also suffers from this lowered score. The second technique is a general approach that can be applied to any keypoint-based architecture. Let's take a look at a heat map with center scores. Taking the training procedure into account, you can expect that 8 connected neighbors of each item to be related to the same object. This fact can be used to improve the estimation of each heatmap value. Therefore, we applied the convolution operation with 3x3 Gaussian kernel to the heatmap. Experimental results show that in our model, the proposed technique improves the localization of peaks and their values that correspond to object centers or keypoints and their scores. The third technique further corrects keypoint locations by calculating a linear combination of the refined and coarse keypoint positions. Our experiments have shown a small improvement than using this technique, and it costs nothing in terms of the performance. The fourth technique is a keypoint heatmap rescoring based on a coarse keypoint location. CenterNet's original idea is that refined location is defined as the closest point to the coarse keypoint position, which in its turn is defined as a local maximum on the heatmap. This can lead to errors when the closest prediction isn't actually the best one. There is an example on the top diagram. The refined location is not the best. We propose to add penalty to the keypoint score in proportion to distance from a coarse keypoint position with Gaussian function. We performed all experiments on the publicly available Deepfashion2 challenge dataset and used the CenterNet-MS COCO model for object detection as the initial checkpoint. We performed experiments with hard glass and DLA34 backbones and Adam optimizer to achieve results on the slide. The combined effectiveness of each post-processing technique is shown in the table. The next technique is added to each of the previous ones. For the challenge, we consider 2 extra inference strategies: fusing model outputs from original and flipped images with equal weights, and fusing model results with the original image, downscale it or upscale it through certain multipliers. The proposed techniques increase accuracy but require several model inferences, significantly affecting the entire processing time. At the final stage, detection results are refined with the postfix, model-agnostic post-refinement method. The method learns the typical error distributions of any other post-estimation method and corrects mistake at the testing stage. We trained a set of 13 postfix models by using the number of classes in the Deepfashion2 dataset. The inference results of our method on the training set are used to train each of the 13 models. Subsequently, we applied trained postfix models to the result and got the final numbers. Note: during all experiments, our target was to increase the keypoint estimation accuracy instead of the object detection accuracy. Also, we adapted DLA34 model to run it on Huawei Mate 20 mobile phone with almost 14 FPS. Thanks for watching. Bye.